Quad 6.6. We have data. Super excited because finally got to start sharing with you some data and some analysis, and this is when this stuff gets really fun. So this is a collaboration with Carl Pablo. He's really been doing most of the hard work in terms of generating the data and especially working out how to get reliable data on the responsiveness of the motors. And this is a new thing for the micromotors in terms of analysis. I think we've all seen kind of like this usual thrust data with efficiency and thrust, but we haven't seen the response time, and I think that's going to create some real insights into how these motors perform and why they feel the way they feel in the air. The part where I want to come in and like contribute to this project is in some of the analysis. And in this time, so we're looking at this 1204-1303 motor because it's the first batch that Carl kind of ran through. But what I want to do is introduce some techniques, and so this is a little primer specifically on functional principal component analysis. And the reason that we need to start bringing in these different techniques is because when we're comparing motors, we're not looking at just one like throttle point and comparing, okay, how do these differ? We're comparing them across a bunch of different throttle points, and you can see that the thrust that we're measuring, it changes as a function of throttle percent. So as we go up in throttle percent, you can see that there is tight spacing down here at 20%, and then it broadens out here at 80%. And so as you go through throttle, this thrust is changing as a function. And so you can best describe this data as a function that that describes these curves. And that sounds great and all, and it's fine, but then how do you describe how these curves differ from each other? And so there's this technique called principal component analysis when you use the functional variant of it that does exactly that. What it does is it models these curves and then says, okay, what is the simplest way that we can explain the differences between curves? I think to further explain that, the thing to do is just jump right in here and show you what this looks like. So if we go ahead and run the functional principal component analysis, we get some reporting out like this, and so what it shows is the mean function, and that is just exactly what you expect. So this is just, if you take all those curves and you average them up, this is what it looks like. And then it shows you that these curves differ according to these other things called eigenfunctions or principal components. And these are like the simplest ways that you can explain them, and then it tells you how much of the variation is explained by these different components. And in this case, the first principal component explains basically all of the variation in between the curves, and the second one is just kind of a trivial amount. In terms of how these principal components actually describe the data, you can see this here, where going from a low to a high value, you can see that it explains how these functions change, where they don't differ a whole lot down at 20%, but expands out and differs more at 80%. And if we actually overlay the data, now these are in green, you can see that this principal component really explains most of the variation here. And just for kicks, I'm going to show you what the second principal component looks like. And it's kind of interesting because it's got this little twist to it where it's sort of like a trade-off between low and high. But it's very small, it's very trivial. And if we kind of overlay these, we can see that it's really not explaining much of the variation, and so we can stop after the first principal component. We can basically toss this one out because it's not really describing much, and so for simplicity, one principal component in this case is good enough. So then we can go ahead and say, all right, well, let's declare some winners. Let's use this. And so I'm just plotting out their one scores, and so now you can see we took those different functions that were changing in pretty complicated ways, or in this case not that complicated, but we simplified it down to one principal component, and you can see that this iFlight Xing motor, and by the way, these are all kind of like around the 5,000 kV range. The Xing motor is a little bit lower and creates some of the differences here, but in terms of thrust, this Xing motor really underperforms compared to the others. It may have some other advantages, but the winner here is this Pyrodrone 1204.5 motor, and you can see that it outperforms compared to the other motors. One of the things to note is that with principal components, this is unitless. This is like relative differences between these motors, but you can't take this score and then turn it into grams of thrust. So it's one thing to keep in mind. So that may not look super impressive because that data wasn't that complicated, but if we move on to efficiency, I'm going to show you a little bit more of the power of this technique, because efficiency data here, these curves are more complicated. You can see that this is still functional data where the efficiency in terms of grams per watt is changing still as a function of power, but that relationship for some of the motors is kind of straightforward, but this Xing motor kind of does some different things. And so then out of this, how do you declare a winner? Well, it's like if you look over here, the Xing motor looks like the winner. Down here, the Xing motor looks like the loser. Well, how do you describe that? Well, that's where this technique kind of starts to become real powerful, because if we go ahead and run it, we get our mean function like we expect, sorted and average, and now we see that we have two principal components that are actually contributing to explaining the variation. The first one's still the most important, but the second one does still is still relevant. It's not like a trivial amount, so we can take a look at these. And so if we go ahead and plot them out, you can see the first principal component is really kind of explaining most of the variation down low. So at low throttles, it's explaining, is the motor better or more or less efficient compared to the other motors, and doesn't really explain a whole lot up high. You can see there is a little bit of trade-off where if you're efficient down low, or if you're not efficient down low, you're going to have to do a little better up high, and vice versa. But it's mainly explaining down low. And if we overlay the efficiency curves, you can see it does explain a lot of variation, but not all of the variation. And that's where that second principal component comes in. So now if we go ahead and plot out the second principal component, we can see now this is explaining that difference that we're seeing up at the higher throttle percentages. If we overlay the data, then we can see that this is now explaining this variation that we're seeing up high and not down low, but this fills in the rest of that explanation of the variation. So now, like we did before, we can plot this out, and we can take that really complicated functional data and just summarize it in two principal components. And so if we look at the first one, which is looking at efficiency down low, we can see the FPV cycle motor. Let's zoom in here so you can see all the names. This FPV cycle motor 1303 does great. The iFlight motor, the Xing, is doing not so great, and then the others are kind of like in between. Maybe the PowerDrone's doing pretty good. T-motor a little bit lower. 1204, not the greatest. And then when we go ahead and look at the second principal component, so this is looking at the efficiency up high, you can see this is where that Xing motor really comes into its own and shows you that high throttle percentages. That Xing motor does really well in terms of producing power efficiently. The FPV cycle motor still does pretty well. T-motor not doing so well, and the others are kind of in the middle. So again, this is relative, but now you have a pretty good relative comparison. And more importantly too is now we have good inputs in terms of looking at modeling and asking some of the questions that I'm more interested in. Is that, okay, if efficiency is differing, what motor parameters are affecting that? And this now gives me good numbers I can plug into equations and model those differences and ask these really interesting questions. So yes, we got some data here. Yes, you can start using this to kind of determine what motor is right for you, but also this is a primer to introduce functional principal component analysis, kind of show how it's useful, and then kind of set you up so that when we go into the deeper analysis, when I say principal component, you kind of know what I'm talking about and it makes sense what I'm talking about. So super exciting start here. So yeah, this is the first batch. These are the 1204, 1303 motors. First batch that Carl started with. We have that big 1103, well, kind of expanded out from there, but we've got that other big motor test that we're going to do, and so we'll do a whole series of videos. For these motors, I'm going to do 2 more videos. Next one is going to be talking a little bit more about response time and response rate and how we measure that and what we're reporting and why. And then the final one, we're going to dig into those different motor parameters and see how they explain or predict the different variations that we're seeing between the motors. All right, hope you're as excited about this as I am. Until next time, cheers.